Hey everyone, welcome back to the day 4, and we're going to be continuing where we left off from yesterday. So let's continue. We were talking about how to build a SNARK part 2 with Dan Bonner from the zk Whiteboard Sessions module 2. We came back to we were talking about PLONK. So there was a few steps in building PLONK IOPs. So step 1 is compiling the circuit and generating a computational trace so that we will have a trace table. So we don't have to, so we just use the trace table and not the arithmetic gates. And the next step is called arithmetization. So we need to encode this trace table into a polynomial. So we will encode the inputs and we will encode the wires and gates. And then we have to prove the validity of the polynomial we are sending. So this is the proving part, is the main important part. So we're going to continue from that because yesterday's video I talked about the arithmetization in the trace part. So here in the proving part there are 4 parts. Let's go through one by one. Correct input. So we have to prove that, we have to check it out if the inputs we are giving out is correct. So how it happens, prover has a public inputs, it checks out the prover, verifier should check it out if the prover didn't swap out the inputs to make the ending correct. So how it is, verifier also has the public input polynomial, and verifier checks out with the prover provided polynomial and its own provided polynomial if they're equal, or if it gives a 0 test. It means like once they are minus, it has to give a 0 result at the end. This is how it's checked. And the next check is gate check. So this is like if the gates are working correctly. We have the addition in the PLONK, there's an addition and multiplication gate. So if it is working correctly, how we do is each row in the trace table, we have each row corresponding to a gate. Gate 1, input, output, input of the left side, right side, and the output. So we will create a selectory polynomial for each gate. It means addition and multiplication will have a polynomial. It should give out, it should technically gate to check if the mathematical operations, if it's addition or if it's multiplication, it should result 0 at the end. This is how it is gonna look like. So left side, right side, and this is the multiplication for left, right, and then the output. So it should check it out at the end that if they are added, it will return 0. So addition will have usually value 1, and the multiplication usually have 0, because once it is working, it returns 0 if they are correct at the end. And so each gate will have its own selector polynomial, and then all the gates will create one big polynomial, so that at the end, if one gate is wrong, the end result will not be 0. That's how it checks out. And wire check is it's quite simple. If the output is correct input to another gate. So how it does, we're just gonna take the position and the value. Let's say this here this position and the value, it should be still correct once it's reversed. What does it mean is here, if we can check it out. Here -1 and in the omega 0, it has to be equal once it's reversed. What does it mean is like we have the value here and we have the value here. So if we try to swap the position, if we reverse the position, if they reverse the order as well, it has to be still correct. So that's how it is checked. This is what I understood. And the last one is output check. So what does it mean is we have the last gate here. We have the very last gate. Okay, it's not here. We have the very last gate, and the very last gate's polynomial should be equal to 0, because if all the polynomials are correct, it has to be 0. That's how it checks out. So technically that's all for today. That's all I learned. I'll try to go deeper in the next lessons, next learning sharing sessions. See you tomorrow.